Hello, my name is Dragan Veselinovic. I work for Green Imaging Technologies, and today I will talk about NMR measurements on unconventional reservoir cuttings. Why do we want to do NMR on cuttings? Well, conventional methods for determination of porosity on cuttings do not give immediate feedback on the porosity while drilling, are complex, expensive, or prone to error, and can't be used on modern drill cuttings, which utilize PDC bits. PDC bits often render the cuttings too small and can destroy the pore network in the cuttings, and this obviously causes problems. Additionally, when doing NMR, we use T2 distribution to determine porosity, and as most of you already know, T2 distribution can be related to pore size distribution, and this gives us some additional information about our samples. Following the T2 based porosity measurement, we extend the NMR measurements on cuttings to T1, T2 maps. In unconventional reservoirs, NMR T1, T2 maps have been greatly utilized for fluid typing analysis. The analysis is done by looking at T1 divided by T2 ratios at different regions of the T1, T2 map. More on this will be said in the later parts of the presentation. Before we talk about the T1, T2 measurements, let's first explain the T2 based porosity measurement of cuttings and sample preparation procedure that was developed in the last couple of years. Porosity is defined as pore volume divided by the bulk volume of the sample. Pore volume is fairly easily measured on saturating cuttings by NMR. However, accurate bulk volume measurement is a challenge. To deal with the challenge, the following equation was developed for determining porosity of cuttings and crushed samples via NMR. Based on the equation, we tease out the bulk volume in a roundabout way by using three alternate volumes that can be measured by NMR. These are referred to as V total, V cuttings plus fluid, and V cuttings. They are illustrated in the diagram below the equation. So on the left here, we have V total, which is basically our sample holding tube filled with fluid completely. This is usually brine, but can be other fluids as well, such as decane or something like that. Then we have V cuttings plus fluid, which is basically our sample holding vial filled with fluid and the saturated cuttings. And then we have a V cuttings measurement, which is basically just the cuttings in the tube, and this effectively gives the pore volume of the cuttings. And when we combine these three volumes in this way, as the equation says, we end up with a V bulk value, which is the bulk volume of the cuttings. So these measurements take anywhere from a few seconds to a few minutes, depending on the samples. In theory, this all sounds easy enough to do, but as we will see later, there are some other experimental challenges that I will explain in the next few slides. NMR measurement only observes the fluid in the sample. So if I wanted to know the bulk volume of the brown cylinder in this example, I would have to do two NMR measurements to determine it. The first measurement would give me the bulk volume of my water-filled NMR tube, which is illustrated by the blue cylinder, and the second measurement would yield the volume of the fluid in the NMR tube surrounding the brown cylinder. The difference of these two measurements would be the bulk volume of the brown cylinder. The determination of the bulk volume of the brown cylinder works in this way as long as the brown cylinder is not porous. As you can see on the right part of the slide, if there's fluid in the brown cylinder, then the bulk volume of the cylinder will be underestimated by these two NMR measurements. Uh, if the cylinder is porous, in order to get an accurate measurement of the bulk volume, another measurement needs to be completed, which is a determination of the fluid in the brown cylinder alone. This measurement is then added to the difference of the first two measurements, and the correct volume of the bulk cylinder is then calculated. Now we translate these measurements from cylinders to rock core plugs. To properly determine the bulk volume of a plug, the fluid within the plug should be measured and accounted for in the calculation. Determining the pore volume of a core plug is a routine measurement with NMR, fairly straightforward. The porosity is then derived for the plug by dividing the pore volume by the bulk volume of the plug. However, we don't usually determine bulk volume of plugs using this method. We usually either use geometry if the plug is a nice cylinder, or we can use gravimetrics or mass measurements to determine the bulk volume of the plug. Obviously, these methods can't be used on cuttings, which is why we had to come up with this roundabout procedure to determine the bulk volume. So for cuttings, we require these three NMR measurements to determine bulk volume, namely the V total, which is our NMR invisible sample holder filled with fluid completely, fluid plus cuttings, and cuttings alone. With these three, we can then calculate the bulk volume of the cuttings. This bulk volume can then be employed in our original equation for porosity determination of cuttings. The problem with this method is that if there's any fluid remaining on the surface of the cuttings when we do the NMR measurements, it will lead to an overestimate of porosity. Fluid on the surface is hard to avoid because we require the cuttings to be saturated with fluid in order to do NMR measurements, or if they're coming directly from the well, they will have either drilling fluid or formation fluid on the surface by default. So dealing with this surface fluid on the cuttings has been the principal effort in this work. So I will spend the next couple of slides explaining that. The reason that the fluid on the surface of the cuttings is an issue is that its NMR signal can overlap with the signal from fluid in the pores of the cuttings, and this can lead to an overestimate of porosity, as mentioned in the previous slide. In addition, as the cuttings get smaller and have more surface area per gram of sample, or more surface area per volume, this problem is enhanced. As you can see from the figure on the slide, the surface water clearly becomes an issue as the cuttings get smaller and smaller. This also illustrates why we don't need to worry about surface fluid when dealing with rock core plugs, as the surface fluid contribution in this case is negligible because rock core plugs have a very small surface to volume ratio. But of course, the smaller the sample gets, this ratio gets larger and larger. To address previously mentioned challenges of bulk volume measurement and surface water removal on the cuttings, the following procedure was developed. First, we designed a special sample holder made out of NMR invisible material, Teflon. As you can see in the photo, this sample holder can easily be compared to a salt shaker. The procedure consists of filling this vial with 2% KCl brine fully and measure its volume via NMR. Weigh 3 grams of cutting sample, vacuum saturate them in this vial with 2% KCl brine. Then measure the volume of fluid in the vial, which is now partially filled with brine and saturated cuttings. So this is how we get the pore plus fluid measurement. We then rinse the cuttings in the vial via D2O by using centrifugation. Sometimes multiple rinses are required. And then we measure the pore volume of the cuttings and any other measurements that are required, such as T1, T2 maps. Ideally, in this last step, we'll have all the surface fluid removed from the cuttings. NMR pulse sequences and parameters used for these measurements are listed in the table. CPMG pulse sequence was used for T2 measurements, and inversion recovery CPMG was used for T1, T2 maps. In addition to porosity determination, T2 distribution can also be related to pore size distribution, which makes this measurement more useful than just the porosity measurement. All data was required on a 20 megahertz Oxford Instruments MQC plus 20 megahertz spectrometer. 20 megahertz as opposed to a lower field instrument was chosen due to very small sample size and low signal to noise ratio of the cuttings samples used. Data acquisition and analysis was done using GIT software. Cutting samples came from a well in Woodford Formation, along with plugs at corresponding depths. Porosities of plugs were previously measured by both retort and Dean Stark. In addition, a few of the plugs were crushed to create crushed core, or what we refer to as pseudo cuttings. The pseudo cuttings were also run through our procedure to further verify these porosity measurements. The accuracy of the cuttings porosity measurement is on the order of 1 porosity unit, so the results were pushing the limits of the NMR measurement capabilities. Low porosity means low signal to noise ratio, making it difficult to compare the results for cuttings versus plugs versus crush samples. The low porosity is consistent with previous retort measurements, but did not match well with the Dean Stark data. There is some suspicion that the Dean Stark method may have dissolved some soluble solid hydrocarbon, aka bitumen. Another consideration is that halite or other evaporites related to formation water may have precipitated in the sample due to high oil-filled brine salinities. The solvents used in the Dean Stark process may have dissolved these salts, but they may have been present when the NMR measurements were done. Here we show a cross plot of cuttings versus plug and retort porosity. The agreement versus plugs is better than agreement versus retort, but neither are excellent. This is mostly attributed to low porosity of the samples and the error in the measurement, which is about plus or minus 1 pu for our cuttings procedure. As I already mentioned, T2 NMR based measurements also give information on pore size distribution. This is why it's important to compare the T2 distributions. So here we show a comparison between plugs, crushed core, and cuttings T2 distributions. So the black trace is a 100% brine saturated plug. The green trace is crushed core, 100% saturated of course, and the red, blue, and gray are cuttings at different depths, also 100% brine saturated. The cuttings, core, and crushed core samples all have similar T2 distributions. Disagreement between the distribution of the plugs and that of the cuttings can be attributed to the fact that the plug is a point measurement, while cuttings is an average over some depth as the cuttings are pulled from the well. A couple more T2 distribution comparisons between plugs and cuttings are shown here. The agreement between these plugs and the corresponding cuttings is excellent. We have a similar shape for each two distribution measured, and there was also a good agreement for the porosity derived from these distributions. So we have plugs 3HA and 3HB shown in black and brown, and then we have cuttings shown in red and blue at corresponding depths. All of these are 100% brine saturated. Now that we've described the T2 based porosity measurement, let's talk about T1, T2 maps. These maps are typically used for fluid typing in unconventional reservoirs. The map can be divided in regions where fluids can be differentiated according to their viscosity by examining the T1, T2 ratio. High viscosity species like bitumen have a high T1, T2 ratio, while low viscosity fluids like water have a low T1, T2 ratio, and they're closer to the diagonal 1-to-1 line on the map, as illustrated in the T1, T2 map shown on the slide. Now let's look at some T1, T2 data that we acquired on plugs and cuttings from this well. In the top left corner, we have a T1, T2 map of a plug. The other three maps were obtained on saturated cuttings from similar depth. This shows that these types of maps can be obtained even for low porosity small samples like the cuttings we were dealing with, although this is probably not practical at low field or 2 megahertz, as the measurement would take a really long time. The agreement between cuttings and plug are satisfactory. Most signal appears in the same region of the map, so the maps are comparable. In this T1, T2 map comparison, we can see that both plug and cutting sample have heavy organics and very little water and light hydrocarbons. So we see sort of a big blob in the top left quadrant in both of these maps. So the left one is plug 3HB at 9,556 feet, and on the right is cuttings at around the same depth. In conclusion, we have successfully determined the porosity of cuttings. T2 distribution comparison of cuttings versus plug data suggests that cuttings can be used for pore size distribution determination. And T1, T2 maps acquired on cutting samples opens up new opportunities in unconventional sample analysis. Thank you for your attention.